Achieving dexterous behavior is the ultimate pursuit of robotic manipulation.
While this is a very simple task for humans, robotic systems have been unable to generalize it across dynamic and multi-contact settings. This work studies a fundamental problem of dexterous manipulation. Given a desired object motion and a model of the mechanics, how can my robot interact in order to achieve this problem? We label this problem contact drive optimization. The state of the art for this kind of problem falls into a dichotomy. The first set of approaches aims to rigorously describe the mechanics involved in the task, leading to unfavorable optimization problems, often unoptimal or poorly conditioned. On the other hand, a second set of approaches approximates the mechanics with the hope of better computational properties at the cost of physically inconsistent behaviors. This work aims to fall in the middle, proposing an optimization model that retains physical accuracy while still providing useful computational guarantees. Concretely, this problem is governed by three main relations. First, rigid body dynamics, encoded through Newton's equations. Second, geometric consistency, forbidding interpenetration between the objects. And finally, contact mechanics, which depend on the object facet and allow contact forces when contact happens. This leads to several reasons why it is challenging to model multi-contact interaction. First, the torque balance equations required to describe the object dynamics involve a nonlinear cross product between the contact forces and finger locations. If both contact forces and finger locations are variables in our problem, that defines a bilinear non-convex constraint. Second, preventing node penetration requires the computation of distance functions, which are often hard to compute and require some form of numerical or free approximation. And finally, the activation of contact forces requires a complementarity constraint between force and distance, making the problem non-differentiable. This work proposes a strategy to mitigate these limitations under the following assumptions.
First, we represent the object and the environment as rigid polygons.
Second, we assume that the object motion is fully known and provided by the user. And finally, we assume that the dynamics can be approximated by assuming rigid point contacts, that nonlinear terms are approximated with other approximations, and that high-order effects are neglectable. Under these assumptions, we can show that it is possible to express this problem under the language of mixed-integer convex programming, an optimization problem that contains both continuous and discrete variables. Under this new language, we can represent each of the linear relations as follows. First, each bilinear constraint can be approximated by covering each non-convex function with a convex polytope under the technique of piecewise Markov envelopes, which retains physical fidelity despite convexifying the problem. Secondly, non-penetration is enforced by constraining the fingers to lie within a set of disjunct convex regions covering the environment. And finally, these complementary relations are represented as discrete decisions assigning each finger to a particular facet of the object. Replacing each of the original relations with this new formulation yields a mixed-integer convex program. This model inherits all the properties of mixed-integer programming, including global optimality and infeasible detection, at the cost of exponential bounds in complexity. We find, however, that this problem can often be solved fast enough through off-the-shelf optimization software. As an input, our model receives an object motion, its description, and a description of its interactions with the environment. Then, our model solves for the required interactions and returns contact locations, contact forces to apply, and the reaction forces with the environment. We also demonstrate how this method can be used to generalize trajectories in different sets of objects, including non-convex polygons. Likewise, we can generate trajectories that are along horizon and involve complex interactions with the environments and the robot, both in sagittal settings, that is, side views, and in trapezoidal planar settings, where friction is happening with an entire object.
Moreover, we show how the results generated by this method also translate to real-world settings,
including both simple primitives such as rotation and grasping, and more dynamic ones such as pivoting. Finally, we also show how we can generate long horizon complex interactions, such as pushing a block and rotating it against a wall. In conclusion, we have presented a global model for contact trajectory optimization. This, however, has several limitations. First, since we assume the object motion is given, the success of the algorithm depends on having a feasible initial trajectory. Second, our model assumes that the problem parameters are explicitly provided to the optimizer, this including object shape, friction cones, and external contact modes. Parsing these elements can be complex and very difficult, especially if we want to go to more complex scenarios. Finally, the mixed integer programming formulation has exponential bounds in its complexity, growing with the number of integer variables. This constrains our problem to be only practical for fairly simple shapes and short to medium horizon trajectories.
Thank you for listening. You can find the source code for this project and more information in the GitHub link below.